everyone. I would like to start thanking the University Astronomy Club for arranging everything and for preparing this nice conference room with subtitles in that screen. Quiero dar las gracias al Grupo Universitario de Astronomía por organizarlo todo, tener esta sala preparada y preparar todo el tema de los subtítulos. I would like to welcome to our regular activities of the Fridays to Roger Wiens and Raymond Francis. I work with them, I know them, and I'm really happy to have them here and welcome them to Valladolid and to these activities. Quiero dar la bienvenida también a Roger Wiens y Raymond Francis a las actividades de los viernes del Grupo Astronomía, que empiezan este curso con esta actividad especial. Hemos estado toda esta semana en una reunión de equipo del instrumento SuperCam aquí en Valladolid y tanto Roger como Raymond han aceptado el darnos una charla divulgativa hoy para disfrute del público. We have been the whole week in a team meeting here in Valladolid and both Roger and Raymond accepted to give a public talk to share with you all the news from the mission. Thank you for being here and sharing your knowledge with us. Raymond Francis comes from JPL. He's expert in automatization of science. He's behind one of the gadgets I really love from Mars 2020, IAGs. This is the capability of the rover to select targets to analyze even without any input from the science team. Raymond es especializado en la gestión automática de resultados de ciencia, en la automatización de actividades de ciencia en Marte, y está detrás de una de las características del rover que más nos gusta, que es la capacidad de seleccionar sus propias muestras que analizar sin necesidad de interacción por operador humano. He's both participating in ChemCam, MSL, and SuperCam, and of course at mission level in Mars 2020. His deputy, let's see if I say this long thing correctly, he's deputy science operations team chief of the Mars 2020 mission. Roger is the PI of SuperCam instrument and also ChemCam instrument. He participated in the Genesis mission. He's a professor at Purdue University and has long experience with Mars exploration. And with no further ado, I give the whole to Raymond. We'll start with the mission status. Thank you.
Sure. So good evening. So I will speak first and then Roger will come after. Roger will give an introduction to the SuperCam instrument and a lot of interesting science results, but I will start with an overview of the Mars 2020 mission itself, the rover, its systems, and what kind of science in general we are doing on Mars. Mars 2020, named after the year that the mission was planned to launch and did launch, is a mission to Mars with 4 sets of ambitious goals that are all centered around the concept of life on Mars, whether it is ancient microbial life that may have existed on Mars. This is something we have still not confirmed, but it's something we're chasing and investigating to see if it was possible, or whether it's the potential for future human life on Mars. In order to look at ancient microbial life, we're going to talk about astrobiology, looking for signs of ancient life, conditions in which life could have occurred. And those things, those chemical signs, those physical signs would be preserved in rocks, which means we will be doing geology. But we also know that we've gone about as far as we can with in situ instrumentation on Mars. And if we really want to answer some of our questions about ancient life on that planet, we really have to bring samples of these rocks back to Earth so that they can be studied in all the laboratories of all the universities on this planet, which have much better equipment than we could ever send to Mars. Even if you will see we have some very impressive equipment on Mars. On the other hand, we're looking at future human life, And so we're doing some things to study the present day environment on Mars and do some technology development that would support future missions with astronauts to Mars. So in support of these goals, we've chosen to go to this place. This is a topographic map of a part of Mars here. It's dominated by this large basin called Jezero Crater. Jezero is named after a town in Bosnia, which is named after a lake beside it. Jezero in Serbo-Croatian and several other Slavic languages means lake. And indeed, this crater held a lake in it, a lake of water, something like 3 billion years ago. There's no more liquid water here now. It's very dry. It's a dry desert. But we can tell that there was a lake here. We can see in the upper left. Roger, do you have the laser? Thank you. We can see in the upper left here a river valley, which is coming into the crater. It's cutting through the rim of this crater. And we can also see an outlet valley. Once the lake filled up high enough, it spilled over the rim of the crater and sent water out to the northeast. And when this river, this valley that today we are calling Neretva Vallis, cut through here, it carried a lot of sediment that had eroded from places out to the northwest and deposited sediment here into the crater, building up this feature here, this alluvial fan. A fan like that is a very good place to look for signs of past life. A lake is the kind of place you look for life here on Earth. You've got water, it's stable. A lake which had enough time to build a large deposit like this, you don't build this in a hurry. This takes many, many, many years to build. So this is a lake that was here for a long time. So that seems like the kind of place that life would have time to arise. But also when you're building a delta like this, you're gradually setting down sediments in gentle layers, in a gentle way, over a long period of time. And that's the kind of place that you could preserve signs of life. It's not a violent emplacement of sediment. So this is where you would look for life on Earth. You would look in environments like this. So we're going to what is probably the oldest lake on Mars and a well-preserved one. Here's another view of the Jezero fan. You can see it's several kilometers across. This crater, we call it Belva crater, is about 1 kilometer in diameter. So here's your scale. So in order to explore an environment like this, we need to be able to bring scientific instruments. We need to be able to move them around to the different parts of this environment. And our solution is this. This is a model of the Perseverance rover, the name that we gave to the rover. It's, these wheels are about 50 centimeters in diameter. It's a very large vehicle. The mast here, the height of the mast is about 2 meters. So compared to me, it's about this tall. It's a very large vehicle. It weighs about 1 metric ton. And it carries these science instruments. These here we'll talk a little bit more. Mastcam Z and SuperCam remote sensing instruments designed to look at things that are far away from the rover. A radar to look below the surface. 2 instruments here that are spectrometers, Sherlock and Pixel, mounted on the robotic arm for measuring things that are from a very, very close distance of millimeters away. And then a weather station, MEDA, which was in fact built here in Spain. And then finally MOXIE, which is our experiment to attempt to produce oxygen from the carbon dioxide atmosphere of Mars. I'll go through those quickly. Here's the remote sensing mast. This is a real photograph now of the rover on Mars, taken with a camera on the robotic arm, looking back at the mast. We have 2 round cameras here. These are the stereo navigation cameras. We use those for understanding the environment around the rover, pointing the other instruments, and driving on Mars. We have Mastcam Z. It's a pair of zoomable color science cameras, which have also some special filters for different wavelengths for studying mineralogy. And then finally, this is the aperture, the 15 centimeter diameter window at the back of which is a telescope, part of the SuperCam instrument. And if you look in here, you can see the mirror at the back. It's a reflecting telescope. That is the horizon of Mars reflected upside down. And I won't say very much more about SuperCam, because Roger will talk in great detail. I will say that it has many different sensing modes, many different types of spectroscopy that it can do. and Roger will tell you all about it. Here on the, I'll talk about the robotic arm instruments briefly. This is a video in the clean room. This is a room that is where the air is specially filtered, where the people are wearing very special clothing to protect the rover from the humans. We don't want to drop a hair or a little bit of skin onto the rover and damage the sensitive electronics or contaminate the spectrometers. And so this is all to protect the rover. And I'm showing you this just so you can see the size of the vehicle and the size of the robotic arm. These are tests that were done. This is the real vehicle. These are tests that are done to make sure that the control of the robotic arm is working properly before we send it to Mars. And this is the room where we build all of our spacecraft at JPL in California. As you can see, it's sped up a bit. The robotic arm does not move quickly. Just a quick view of the kind of data that we get from these two instruments. Sherlock is a scanning laser spectrometer working in what's called Raman spectroscopy and also a type of luminescence spectroscopy. But basically, you can shine laser light on the surface, excite the minerals and the molecules in the rock, and from the wavelengths that come back, you can tell the mineral and crystal structure of this material. And Pixel, on the other hand, is an X-ray spectrometer, which is sending X-rays, high-energy radiation, into the rock, exciting the atoms, and from that we can get the elemental composition. Which chemical elements is this rock made of? And between the two, if you overlap them, you can get, this is an example that was done here on Earth, you can tell by the hammer. But if you overlap them, you can tell a great deal about the composition of a rock. These areas here, these are only a matter of a few millimeters across. This is the size of a fingernail. And they're making hundreds of measurements across that space, extremely fine scale measurements. But we can only do that in a few places. And to understand the broader environment, we have instruments like the mass cams and the SuperCam. To understand the area underground, we have a ground penetrating radar built in Norway and contributed to the mission. And this helps us understand the context of what we can't see below us. When we're driving over loose soil and sand, we want to find the rocks underneath and the structure of the materials there that we can connect to what we see on the surface. And again, the weather station, wind speed and direction, temperature, humidity, the amount of ultraviolet and visible radiation falling through the sky down to the surface. And this is making measurements all the time on Mars. We have a long record every day, basically, since landing. But we don't just observe the atmosphere, we also modify it very slightly. This MOXIE was a device designed to demonstrate through a chemical process that you could take the carbon dioxide in the Martian atmosphere, break the chemical bonds in it, and recover the oxygen to form oxygen gas. If you ever wanted to send astronauts to Mars, you could carry all the oxygen with you, but that's very heavy. All the oxygen they would ever breathe, or you could make it in place. Oxygen is also very useful as a fuel, particularly for rockets if you ever wanted to leave Mars afterwards. And we were able to demonstrate that we could make about 120 grams of oxygen, which doesn't sound like very much, but it's enough to fill a couple of cubic meters at this pressure, so it's, you know, it's a start. Astronauts would need a much larger device. And we have one little last thing here, which is we also carried a second robot, a flying robot, a helicopter, an autonomous helicopter. This is it folded up. These are the blades of the helicopter. This is a solar panel that powers this electric helicopter. And this below is the rover. In that same clean room with the video with the robotic arm, this is in the same room. The rover is upside down. Here are the wheels. Here is the antenna for the ground penetrating radar, and various other equipment here. But the helicopter is bolted to the bottom of the rover, and then it will be covered with a protective shield for landing on Mars. So this completes our set of tools. Now, I don't have time to talk about the entire decade-long process of building a mission like this, but it takes a long time. The plan to build this mission began as early as 2013, ahead of a 2020 launch date. And it was not until 5 years later that we had selected actually where on Mars was the right place to land. Through that whole decade, we're designing and building the rover. We don't launch until 2020. And then it takes us from July 2020 until February of 2021 just to get to Mars. It's many months to get there. And now we're in what we call the surface operations phase, and this will continue until we're done. As I say, about 7 months, almost 600 million kilometers, and then it reaches the atmosphere of Mars. It doesn't go into orbit. Some missions will go to Mars, enter orbit, and then eventually land. This mission goes directly into the atmosphere after its cruise from Earth. At about 126 kilometers altitude, it hits the top of the atmosphere. It's enclosed in this case here, which protects it. There's a heat shield here, which protects it from the tremendous energy of decelerating and ionizing and pressurizing the atmosphere in front of you. This part here with solar panels which power the rover during its trip and control its attitude during its trip from Earth, this is discarded just before we hit the atmosphere. When we hit the atmosphere, a very complex process with multiple steps takes place over about 6.5 minutes from the top of the atmosphere to the ground, where first it guides itself through the atmosphere, it uses inertial navigation, and it controls itself to follow the desired path so that we can go to the landing site we want, even if there are unexpected winds or unexpected changes in density in the upper atmosphere of Mars, which we don't understand very well. And then eventually it's slowed down enough and the heat has dissipated enough that you can use a parachute, and this slows you down a great deal more. But the parachute is not enough. The atmosphere of Mars is so thin that a parachute is not enough to land safely. You still come down too quickly. And so at some point we have to remove ourselves from the parachute and then come down with rockets. But if you have rockets to take you all the way down to the ground, those rockets are going to make a tremendous mess. They're going to blow rocks and soil and dust all over the place, and this is a risk to the rover. And so just before we get to the surface, the platform with the rockets lowers the rover on cables, and then the rover touches down on its wheels several meters below the rockets, which is meant to keep the rover safe from the rockets. And then we cut the cables with the rover safe on the ground, and this thing flies away and crashes somewhere, away from the rover, to keep the rover safe. So that's the process. And I show you this process just to say, one, it is very complicated to land on Mars, but two, so that I can show you this video of what it looks like from the camera on the bottom of the rover as you hit the top of the atmosphere and are now descending on the parachute. There's the delta fan here, and this is the floor of the crater. You recognize this feature. I'll show you this again later. We're going to touch down just up here. And it is finding a safe place automatically. There's computer vision that is detecting a safe landing site. There's the wheel, and there's the ground. And this is sped up. This takes about 3 minutes, this whole process. But this is all done automatically. When this happens, at the speed of light, Earth is 7 minutes away. And this only takes 6.5 minutes. The part that you can see with the heat shield removed takes only about 3 minutes. And so it's not possible for people on Earth to intervene in this. The robot has to do this all automatically. Descend through the atmosphere, find a safe place to land, and touch down. Now, after it touched down, the first thing it did was send back a couple of images. One of the very first images we got was this one. And this is an image from the rocket platform, looking down at the rover still hanging on its cables, just a few meters above the surface. And you can see that the rockets are impinging on the surface. They are blowing sand and dust away. The rover is just about to descend into that. Had the rockets been any closer, it would have been very dangerous for the vehicle. That's why we have these cables. But when we saw this picture, we were very excited. You can imagine, we had been working for years to make this thing together, and this shows that we've almost made it. In fact, we only get this picture if the rover is safe on the ground. This picture is from just before it touched down. Everything looks right. The wheels have deployed, all the instrumentation is here. You can see even little details that everything is in good shape, and we know that the rover has survived its trip to Mars. People were very excited. It was still the time of COVID-19, and so we couldn't hug each other, but we were like hugging across the room, high-fiving without touching. This was an image that made people very excited. Because we landed safely on Mars, we can take a picture like this. This is a mosaic of many images here, taken again by a camera on the end of the rover's robotic arm, showing the rover and also the helicopter after we had deployed it here on the ground. So this is a few weeks after landing. The rover is still nice and clean. Today it's full of dust and dirt. I'll show you another view of the helicopter. This is the helicopter standing on the ground taken by the rover some distance away. This is a view of the shadow of the helicopter taken by the helicopter looking straight down. It is a camera whose job is to watch the ground move underneath the helicopter so that it can detect its own motion. And this, I called it an image, but actually it is a video of the very first flight ever accomplished on another planet. It takes a few seconds here that the helicopter will start up, and it will climb to an altitude of about 3 meters. Here we go, the blades are turning. This is a video taken by the rover, and it climbs up to a few meters. It's going to rotate 90 degrees to show that it can control itself in flight. There it is. And then it's going to descend and stop on the ground, almost exactly where it took off. And it's using this camera right here to control its position and hover in place so that it doesn't drift. And there it is. That is the entire duration at 1-to-1 speed. That's exactly how long it took. It's only a few seconds long. But that's the very first flight that anyone ever made on another planet. We made about 73 more flights after that. And many of them were longer and farther and more ambitious, but this is the beginning of aviation on Mars. So I'll do just a quick overview of the science mission and the exploration that we have done. Here's a view again of the western part of the Jezero crater. You have again the crater floor where we landed out here, right about there at this little mark. This is that fan, that alluvial fan. Sometimes we call it a delta. Here's the crater rim with the Nereid Vivalis cutting through it. And we're going to make explorations of each part of these. Very quickly, so we did a crater floor campaign where we looked at that feature that I showed you in the landing video. There's sort of a couple different terrains here that the geology team has mapped differently. And they were very interested in understanding the composition of these. Are these igneous rocks made by volcanic processes, sedimentary rocks made by deposition in the crater? It was actually very confusing from orbit. We weren't sure, and we went with the rover to find out. I'll let Roger tell you the answer, because SuperCam had a lot to do with figuring that out. After we investigated the crater floor, we drove the long way around here. The road was easier this way, so we went around this terrain and then began to study the front of the delta. And here we found, a little bit closer up, actually rocks that look like they're from a delta, rocks that look like they were deposited in a lake, sandstones and conglomerates, the kinds of things that are deposited from sediment falling out of a river. In the case of the conglomerate, sediment of very different sizes. But this is deposited in water, absolutely. And in fact, in shallow water, in some of it. So then we were able to climb up on top of the crater and begin to understand, not on top of the crater, on top of the delta fan, and begin to understand these materials, look at it from another direction. And we can see a great diversity of terrain, a great diversity of materials up here. Here, perhaps in the projection, you can see these curving lines. Very, very pronounced feature of parts of the fan top, whereas over here there's none of that. There's lots of loose, blocky material. Very different terrains on top that would have been deposited in different environments. So there's clearly a change over the history of this place, probably several times. These kinds of curvilinear features that I showed you in the previous image are the kind that form when delta has deposited itself and the river is now putting new material on top and cutting through old sediments to deposit new ones. You see this on Earth all the time, and the big famous deltas, the Mississippi, the Nile, the Brahmaputra. It looks very similar. And this is just an example of what that looks like from the side. You can see these layers here expressed. This is exactly what you would expect if you had a delta in a big lake like that. And then finally, we're now at the crater rim at the edge of the crater here, just beginning to explore beyond it. And I'll show you a place that we call Bright Angel. It's named after a place in Arizona. And here we have delta-type, margin-type, lake shore materials in contact with some other things. This looks like the lakeshore materials. This looks like something else. It's very different in texture and in color, and you can see the bright line linear features through here. We call these veins. These are not present here, but they're very present in this rock right beside it. We're right in contact with two different things. Geologists are always very excited by this kind of thing, when different things are close together. And in fact, if you look very close, this is now from that camera on the robotic arm that takes the selfies of the rover, where they can also put it down and take pictures of rocks, which we do more often. And this is from only a few centimeters off the surface, looking very closely. And here are the veins that I showed you in the previous image. And you can see that inside these veins, which are made up of a kind of salt, calcium salt that would have been deposited here from flowing water, also there are some minerals. These are olivine crystals of the kind that would only form deep inside the planet. And then between the veins we have this material here, this reddish material, which has all of these little spots, which have rings of dark material around them that show signs of chemical reduction, zoning of elements, and the preservation of the kinds of chemistry that could be evidence of expressing of energy. If there had been bacteria here, that these are the kinds of energy pathways that bacteria can exploit. And this stuff is recorded here in the same place as the Sherlock instrument on the arm is recording organics being detected with the Raman spectrometer. Putting all of those in the same place is a very interesting and very exciting sample, which we took only a couple of months ago. Now, speaking of samples, that's what I said we were here to do on Mars, one of our big goals. Here's a map of all the places that we've taken samples, including that last one that I showed you right here at Bright Angel. When we take samples, it looks something like this. We have a drill on the robotic arm. This is a view from a camera under the rover. Here's the front wheel. The drill pressed up against the rock and then grinds its way down and pushes in and removes a cylinder of rock, maybe intact, maybe broken into pieces. If you look at the end of the drill, this is the drill bit, and there's the rock sample inside. Another view of it, again from the camera on the end of the robotic arm, looking back at a place where we have drilled. Here's two holes in the rock, and we've taken two samples, and we've put them in the front of the rover here. Inside here is where we store those samples. We have taken a great many samples at this point. We have 43 total tubes on the rover, of which 28 have been filled with samples. 22 of them are rock cores. 2 of them are regolith, like soil. 1 of them is an atmospheric sample. It's just air in the tube. And we also have 3 what are called witness tubes. These are tubes that don't have any sample in them, but they've been processed through the whole machinery in exactly the same way as this tubes with samples, so that if there's any contamination, we can help understand where that came from. That's where we're at with sampling. This is where the mission is going next. We're going to move south along the crater rim. We've identified a number of safe paths, a number of different geological units that we can explore as we do this, and we're going to fill the rest of our sample tubes out here. And I've filled all of my time, so now it's time for Roger.
Thank you, Raymond. It's a great pleasure to be here. It is my second time in Valladolid. The first time was in 2017 when I was here and we were still building the rover and all of the instruments. And as I will tell you, Valladolid played an important role with the calibration target assembly for the SuperCam instrument. So I'll tell you about that in just a few minutes. Let's see, I think we have to still switch the slides. So the, yeah. And so there was Professor Fernando Rull, who was here, and he accepted the idea to build the assembly of the calibration targets for the rover here, and with colleagues in Spain, and also working with Jose Antonio as his manager. Let's see. Sí, gracias. So we started with this instrument in 2014. This was the proposal that we sent to NASA, and it showed an instrument that could shoot a laser and study targets that are some distance away from the rover. It's showing 2 colors of laser beam, one red and one green. They do not actually happen at the same time, but to show them in the picture, we showed it like this. And it shows several different techniques. So I'm going to walk you through that so you will get an in-depth view or understanding of one instrument on the rover. So here is the mast unit. The top of SuperCam sits up here. And then it's connected with a fiber optic to the body unit where we have sensors and electronics. And then here's the calibration target. I'll show you another picture later. And then this instrument has 3 spectroscopic techniques. So I'll show you more in depth in just 1 minute the laser-induced breakdown spectroscopy. So we use the infrared laser to get the chemical composition by shooting this laser. And then we use another technique with the green laser Raman spectroscopy. And this gives us the mineral or molecular composition of the rocks. And then a third technique uses sunlight and reflects the sunlight back to the instrument. And in the infrared, we can tell mineralogy of the rocks from that sunlight reflected back. Now there's also a high-resolution camera, and this takes the highest resolution images from the rover. And so you'll see some of that in just a few minutes as well. And then one final part of SuperCam is the microphone, and I'm also going to give you examples of what we have heard on Mars for a complete experience of what we see and hear if there was a human on Mars. So here is the close-up image of this calibration target assembly. It has something like 27 different targets. These all have different compositions, and we analyze them on Mars to make sure that everything is working correctly and we know what the right compositions are. There are some different colors here for the camera. They are surrounded by magnets, actually, to keep some dust off of them, but there's also magnetic dust that collects around them. And so when you see this on the rover, and this was just taken in July recently, it looks the same, except there is a lot of dust in circles right around these targets here from the magnets. So we have shot this many times. We do it at least about every week on Mars, and it is playing an important role. So thanks to Valladolid. So here is the other parts of the SuperCam instrument before we put it on the rover. So here's the body unit. Here's the mast unit. And I am looking through the glass wall of a clean room here. Okay, so I have a short video just to demonstrate the LIBS technique. So let me start that. And you do not see the laser beam itself. This was on the previous instrument ChemCam. And we're going to shoot at a rock about 2.5 meters away. In fact, it's an iron pyrite crystal. And you will only see the flash of the LIBS technique. There you see it, right there. And so it is optically bright. We can see it with our eyes. And so when the rover was about to land, the newspapers, the media, the television, they wanted to know, are you really blasting Mars with this laser? How big is it? And you know that the media always exaggerates. So we saw this picture on the internet. It's not what we really do. So this is what we scientists in fact see. So this is the color spectrum. You can see the rainbow color here. So it goes a bit into the ultraviolet, and it goes a bit into the infrared, and we know by the wavelengths of each of these features what element they are representing. So you see all of these elements that are present in the rock or the soil that we shoot with the laser. So that's one technique. We have these other techniques as well. I will not go into as much detail with those. One of the features of SuperCam, it has all these techniques, but the LIBS technique, also the shock wave from the flash, from the laser, blows the dust away. And so you can see that physically the dust is all over here. This is a target on Mars. We have shot these points. And the dust has all gone away over here. And so now we could use all the other techniques in the same place otherwise we might just see dust. But now we can see the rock itself with these other techniques. So when we got to Mars, I want to show you what our imager does with SuperCam. This is the vista that we have from the landing site. And you know that one of our top priorities was to study the delta. It's more than a kilometer away over here on the horizon. So I'm going to show you this location right here, which is the front of the delta. And so here is a set of 5 images from SuperCam that are assembled together. SuperCam is like a telescope, so it takes telescope-looking images that are round, and we put them all together. And so here is our first good look at the front of the delta from the landing 3 years ago. And what do we see? You might expect that a lazy river would bring a bunch of mud and a bunch of silt, and it would all pile up here. But instead of just silt, we saw this. We saw large boulders, large rocks. Several of these are larger than a football. And this is more than 2 kilometers away. So we have some amazing vision with the SuperCam instrument. And so this became the first scientific paper of the mission to explain that there must have been rapid floods that happened, some violent floods to cause these boulders, these large rocks, to come all the way down the river. So the climate on Mars might not have been always calm or stable. Maybe there were glaciers that were melting or some other reason that we had a lot of water running at a time. Now, Raymond told you about the formations in the floor of the crater. The Maz formation was one that is igneous, typical igneous rocks. But when we drove into the Zeta region, part of our purpose with SuperCam is to study the composition of the rocks. So here is magnesium, one element. And so you can see that the abundance of magnesium is low in the first 180 days after the landing. But as the rover drove into Zeta, right here, all of a sudden the magnesium goes way up to almost 1/3 of all of the composition. And this is typical of one type of rock, and it is called olivine. And so here is the SuperCam image, just looking 2 meters away here at this rock. And we could see the mineral grains very well. They are large. They are about 2 or 2.5 millimeters in size. And these are all olivine crystals. And it's a great view of that. It's a bit in false color. They are really a nice green color. And so this tells us that these crystals were more dense, and in a lava chamber, they sank to the bottom, and they all collected together here in what we call a cumulate. So a very interesting geologic formation there. We have also, along the way, found some rocks that are almost exactly the opposite. They are very rich in aluminum and silicon. Now this happens with a lot of heat sometimes, but also with a lot of water. And so in places on Earth where we have a tropical climate or some warm water, we get these kind of rocks. They are kaolinite is the mineral. We also saw some spinel in here, and we're not sure where these came from because they are just sitting on the ground. But we are going to look for the source of these and look at where these might have been heated, possibly through another impact that might have caused the heat that would cause these to transform from normal rocks into almost a clay mineral called kaolinite. Never before seen on Mars. We've done a lot more investigation of the compositions with our spectrometers of the rocks, but I want to tell you about the microphone, which has also been fascinating. So SuperCam has this microphone here, and it's to study the physical properties of the rocks. When we fire the laser, it makes a sound, kind of a zap when the flash happens. And we can tell by how the sound evolves over many laser shots if the rock is hard or soft. So we have used that a little bit, but we've used the microphone even more to study the wind and the turbulence of wind on Mars. And so just a couple of examples here of some sounds. So I think you have maybe seen some pictures with what we call in English dust devils. They are turbulence in the atmosphere that raises a lot of dust. Well, there was one day when we had the microphone turned on SuperCam, and the cameras were taking pictures occasionally, and in fact a dust devil came directly over the rover. So I want to show you that experience. Let me start the recording. So you will see the air pressure, and that is right here, goes down. You might hear this. And this was when the dust devil was very close, and the dust was all around the rover. And at that time we could hear a lot of noise from the wind. And then it's quiet because it's low pressure and not much wind right in the middle. And then as the other part of the dust devil goes by, then you can hear the wind going the other direction. So it was amazing to experience this through the senses of the rover. There we go. One other thing that we heard on Mars was the helicopter Ingenuity. We were not sure if we could hear Ingenuity because Ingenuity was not allowed to come near the rover. Its closest was about 80 meters away, and the sound does not travel very far on Mars. So we did listen one time when the helicopter was flying. So here is I'm not going to give the recording because it's kind of quiet and a little bit boring to some of our ears, but it was exciting to some of us. But here is the different frequencies. So these are low pitches at the bottom of this plot and higher frequency or higher pitch here. This is time here. So we started the recording, and there were some wind gusts, and they are low pitch, as you could just hear. But here is the buzzing sound from the blades of the helicopter. The helicopter's blades spin at 84 times per second, 84 hertz, and that's exactly the pitch that we heard, the sound frequency. And so we could hear it here, and we could hear the first harmonic that is twice as high a pitch right here at 168 hertz. And we could hear it going away, and it got very quiet when it was farthest away, and then it returned over here. And so it's great. We could even hear these details. So we have been doing other studies of turbulence with the microphone as well, and just having an exciting time with both with the images, the spectra, and the microphone with SuperCam on Mars. Oh yeah, I wanted to also say that the speed of sound on Mars is only 2/3 of what it is on Earth. And in fact, there's a very strange phenomenon because the high-pitched sounds travel faster on Mars than the low-pitched sounds. So imagine going to a concert on Mars, because it would sound very strange. The high pitch comes first and then the low pitch. So we are very fortunate on Earth that we don't have such a phenomenon. Okay, I want to also say that we had a wonderful time, excellent time in Valladolid. This is our team in the Palacio with the regent of the university here who welcomed us the first morning. And you can see we have about 50 people, maybe almost 60 people from France, USA, España, Canada, Germany, and Denmark here for this, and then about 15 people online as well. So thank you very much for your hospitality in Valladolid, and thank you for your attention. Muchas gracias.